Hi guys, let's have a look at solving systems of linear simultaneous equations in two variables, and we're going to do this in two parts. Okay, there'll be a part 1 and there'll be a part 2 because this is a big deal and I need to explain this to you in a way where you can really get this with confidence. Okay, so it'll be split into two parts. Let's go. Now, when solving simultaneous equations, which you've been doing since year 9 I think, in two variables x and y, we have always considered, you and I, the situation where there would be only one solution in x and y, right? One point of intersection, if you look at them in a graphical sense, is what you mean by the simultaneous solution of both equations, right? Where they're both simultaneously correct at the same point. So, if we consider, as I say, if we consider representing the two rules graphically, then it becomes clear that knowing that the simultaneous solutions for x and y occur, or solution occurs where the lines cross on a graph, then there actually are three, not one, but three possible solution scenarios. I know, gripping, isn't it? So, let the two rules be y equals m1 x plus c1, that is the gradient is m1 of the first rule and the y-intercept of the first rule is c1, and then similarly y equals m2 x plus c2 for the second rule. Now, okay, case A is where the gradients are unequal, right? If the gradients are unequal of two straight lines, guys, they are going to meet. They will definitely meet, and they will only meet at one point. There is one simultaneous solution in x and y where the graphs cross, okay? That's the one that you've been used to doing and I've been used to showing you how to do, okay? However, waiting in the wings, there are two more scenarios grouped under what I call case B. I know, it's gripping. So, here's case A. You know that one, don't you, right? This is two gradients with two graphs, two rules, right? Y equals mx plus c type rules, linear rules with different gradients, and therefore they cross at one point. That is the simultaneous solution where both of those rules are applying at the same point in x and y, okay? And there's only one possible point where that can occur. Now, case B, this is the gripping one here. If the gradients were equal, if the gradients are equal, then the lines are parallel. That means m1 equals m2, alright? Now, there are two subcases of these parallel lines for us to consider. First of all, I'll call B1. This is where the y-intercepts are different. The gradients are the same, but the y-intercepts are different. That is, C1 is not the same as C2. Case B2 is the situation where the y-intercepts are actually equal. C1 equals C2, alright? Now, this one over here means that these are like train tracks or tram tracks. There's no solutions here. They're parallel lines which will never meet because, I'll show you, like that. You see, look, these ones are parallel, but C1 is different from C2. So M1 equals M2, in other words, the gradient or the steepness is the same in each case, but the y-intercepts are different, therefore they never, ever, ever meet. Got it? Okay, now this one here is actually the same line. I know, it's shocking, isn't it? Infinitely many solutions in x and y because the lines are on top of one another. They intersect everywhere. So there you are, look. There is M1 equals M2. I've tried to do them as a red and a blue line for you. And C1 equals C2. They have the same y-intercept, therefore they're the same line. So therefore, yes, they intersect with each other everywhere. So there's infinitely many solutions, right? So these are the two cases, or the two subcases of case B, where the gradients are equal, which we're going to consider in some depth as we go through this video, okay? Now, case A is the one where the gradients are unequal. Let's do that. And we'll solve it, and we'll just, to be complete, we'll do it rigorously. I've given you that example. We'll do it firstly without matrices, and secondly we'll do it with matrices, right? Call one of them equation 1 and one of them equation 2. Right. Now here's the non-matrix solution. Now you multiply, you know how to do this, you've been doing it since year 9 or 10. So you multiply, I'm going to do this one by elimination, I think, and multiply equation 2 by 3. Yes, yeah, I know. It's easy. But I'm going to show you anyway, okay? Then I'm going to add 1 and 2a. I call this one 2a because I've multiplied it by 3, so it's kind of like daughter or son of 2, if you like. And you add 1 and 2a. By the way, you document everything you do, don't you? Yes, I hope you do. I keep telling my students to do that because they never do it properly. So I've got to harp at them. So please document everything you do. So what do you get? You multiply, adding those up together. Yes, 5x equals 10, therefore x equals 2. Great, it's great, isn't it? It's easy. So now we sub x as 2 into either of those equations, it doesn't matter. And we get that if I put it into equation 2. Therefore y would be minus 3, therefore. Now that's it, that's the solution. That's the one simultaneous point. That's the one point at which both of those rules are simultaneously obeyed, right? NB. That there is only one simultaneous solution in x and y can be readily determined by, yes, if you divide, providing these equations are in the same form, that's something x plus something y equals something, right? You can basically just do a quick and dirty look at it by dividing through by the y coefficients, right? If you do that, right, the x coefficient then shows if the gradients are equal. So I'll show you. Look, I divided through by the y coefficient, so I got a plus 1 in front of the y now, right? So 2/3 of x there. Now, this one here I divided through by the y, whatever the y was in equation 2, what was it? It was just minus 1, wasn't it? Minus 1, so I get minus x, and I get, what do I get? Minus 1 times x plus 1 times y is minus 5, that's right. Now, you just need to look at these now. Are they the same? No, they're not the same, therefore the gradients are different. The gradients are different, then the lines are going to intersect. That's what I'm saying to you. Okay? Make the, yes, so that's a little summary there in green. Make the y coefficients equal. If the x coefficients are different, then M1 is different from M2 and there's only one solution. Got it? Good show. Let's keep going. This is the matrix solution now. Oh, gripping. Grip. Super grip. Now, what do we do now? We've written this out in matrix form now. So that's 2x plus 3y is minus 5. 1 times x minus 1 times y is equal to plus 5, which is exactly what we had up there. You right with that? Now, how do you solve that for x and y, ladies and gentlemen? Well, I like to use this convention here. I like to rewrite it out like this. Capital A times capital X equals B, where capital A is that beastie there, that square 2 by 2 matrix, and capital X is just the matrix X and Y, okay? And B was, what was that? That was that thing there, right? Now, we get, so therefore if AX equals B matrix equation, we do the old multiplying by the inverse trick, to get rid of the A, dissolve the A, as it were, right? Make that into the identity matrix. You do that on the left-hand side of both of these equations, where you can get, when you can get at the A, right? Multiplying it by its inverse. So the left-hand side both equations, remember that the order matters. That'll just become I times X with the identity matrix times X, because matrix times its inverse gets you the identity matrix, which is the same as just a 1. If you like, in a matrix sense. So they'll just get as x equals the inverse of A times B. There she be. Now we just got to do that, okay? So I've got to work out the inverse of A, right? So the determinant of A was AD, that's minus 2, minus BC, right? So that looks like minus 5 to keep us alive. Now we've just got to do the old fiddle with the numbers inside the matrix now. So the inverse would be minus, what have I got? Yes, 1 over the determinant, so that's minus a fifth now. Now we reverse the A and the D entries, right, from what we had here, up here. So we reverse those two and we minus these two. That's what we do. So there's your inverse of A, and therefore inverse of A times B would be all of that. Does that work? That's a 2 by 2. That's a 2 by 1. And the answer will be a 2 by 1. That's right. according to our rules of multiplying matrices together. And what do we get? Aha, very nice. And what is that? What is that? What is that? Oh, goody. It's the same. It's the same. Otherwise we'd be in deep trouble. So therefore that's the x, that's the y. We're flying high, my oh my, and that gets us that. Yeah, so therefore that's the little beastie we want. That's it. So I did it matrix-wise. So now remember, this is case A. Case A today, this is where the gradients are not equal. So now we're going to move right along now to case B1, I think. Yeah, case B where the gradients are equal, the lines are parallel, M1 equals M2. There are two subcases, we'll do B1 here, where the y-intercepts are different. That C1 is not the same as C2. No solutions, parallel lines, and they never, ever, ever, ever meet, right? Now, this is our example to use here, alright? Let's go for it. Now here's the non-matrix. We're going to divide both sides by the y coefficient as I showed you in the last screen. Okay, so I'm going to get that. Do you agree with that? Yes, you do. Well, that's good. Okay, now let's do the second one. Dividing by the y coefficient, we get that. Goodness gracious me, look, the gradients are the same. The gradients here, according to the way I showed you, if the x coefficients are the same, then the gradients are the same. These lines are parallel, guys. These lines are parallel. And furthermore, you can see over here, these numbers here give you the coefficient, the, what do you call that thing? The the y-axis intercept, right? That is the y-axis intercept. That is the first one. That is the second one. This is not actually the gradient itself, it's actually the negative of the gradient. Don't worry, you just need to check whether those numbers are the same, and they are the same, therefore the gradients are the same. This actually gives you the value of the y-intercept, yes, and they're different. So these are parallel lines. I can tell you right now they're never going to meet. There'll be no solution to that. No solution. Same gradient, and those things there, different y-intercepts, yes, the parallel lines never meet. So there's no solutions, but if you want to go through the whole process of doing it, and if what I've done is just confused you, put both of the equations in y equals mx plus c form, and it will become clear for you to see. Look, okay, solving them for y, right? Not mucking around now, solving them for y. That's what you get. Now you can see quite clearly that the gradient, that is the gradient now, that is minus 2/3, and these y-intercepts are different, so therefore they're parallel lines which will never meet. If you try to solve it, you get a contradiction, you get a nonsense, right? So I'll show you. If you make y from the first equation equal to y from the second equation, you get that, right? Now, if you then fiddle with that, that'll cancel, and you'll get something ridiculous, like minus 5 over 3 equals minus 5 over 6, which is obviously not true. So therefore, this is a contradiction, and therefore there's no solution. Okay? So that's the non-matrix method. Now we'll do the matrix method, okay? Okay, here we go. Dividing both sides by the y coefficient. What do we get? Just having a look at it. Now, what I've told you in the previous screen is if the ratio of the x to the y coefficients is the same in both equations, which it is, then the gradients are equal. All right, then the gradients are equal. Furthermore, not only that, but the determinant of the 2 by 2 square matrix in the matrix equation, or if you like, leaving it in its original form, will be 0. Will be 0 because look, you can see 2/3 times 1 minus 1 times 2/3 gets you 0, or alternatively 2 times 6 minus 3 times 4 gets you 0. Alright, the determinant is 0, whichever way you cut it, guys. Now, if the determinant is 0, that tells you there is no solution. There is no solution, okay? So this means that this thing, this beastie here, that one there, or this one there if you like to do it that way, without doing the division first by the y coefficient, therefore these are singular matrices with determinants equal to 0, and therefore there's no solution. They have no inverse, and therefore there's no solution. That's what that shows you, okay? That's the matrix way of doing it, guys. That's the matrix way of doing it. Okay? Let's go on to case B2 now. This is where the gradients were equal again, but this was the case where the y-intercepts are also equal. They're the same. So it's the same line, and we have infinitely many solutions in x and y because the lines are on top of each other. They're basically intersecting everywhere. So if we have a look at this case here, this looks a very, very likely customer for what we've just been talking about, okay? Because if you look at them, guys, if you cast your beady eyes upon this creature, this equation here is exactly the same as this equation here. This second equation is the same as that equation there because it's just this equation multiplied by -2. Ha! You see? I've been sprung. So let's do the non-matrix and the matrix solution to this, okay? Now, again, for the non-matrix thing, we're dividing both sides by the y coefficients just to get a handle on what it's doing. That's the first one, that's the second one. Yes, the ratio, look, the ratio of this coefficient to this coefficient in both equations is the same, right? That's the same. And not only that, but they are the same numbers, right? They're the same numbers, so they've got the same y-intercept. Same gradient. If those numbers are the same, it's the same gradient. If those numbers are the same, you've got the same y-intercept, right? So they're parallel lines which never meet. Never, ever, ever, ever. Well, actually, no, they always meet. Of course, they always meet because these guys are the same y-intercept. So they're two lines right on top of each other, parallel and right on top of each other. There's infinitely many solutions. If this is confusing, yes, as we did last time, put the both equations in y equals mx plus c form, and you will see very clearly what we've got. There it is. They're the same equation, guys. Look, they're the same equation. So if they're the same equation, then trying to solve these produces a trivial, obvious solution. So look at that. If I've made the y's the same, right? I've made this y equal to this y, therefore made the right-hand sides the same. You get that. Oh, wait a minute, I've just done something wrong. Abracadabra, I just fixed up these minus signs were missing for some reason. I must have been in a coma when I did it. So therefore that's correct. And therefore you get a very, very silly, trivial solution to that, wouldn't you? Yes, you just get that cancels, and therefore you just get 0 equals 0. Well, that's pretty obvious, isn't it? So it doesn't really do much to help us solve it because basically there's infinitely many solutions. See? Let's do the matrix way now. Again, dividing both sides by the y coefficient just to get a handle on what's going on. You can see if the ratio of the x to the y coefficients is the same in both equations, which it is, then the gradients are equal, right? Furthermore, the determinant of this matrix here, or if you didn't bother to do the dividing by the y coefficient, if you just left it in its raw form, the determinant of this would be 0. And if the determinants are 0, therefore they're singular matrices with determinant equal to 0, therefore they have no inverse, and therefore there's no solution to the matrix equation. There's actually infinitely many solutions, but the matrix equation comes out with a no solution result. So basically that's that, alright? That's how you do that. Now, have you noticed now that for this case B situation where you've got parallel lines, if there's no solution or if there's infinitely many solutions, the determinant of the square matrix which is produced by these equations here is always 0. Okay, so that's how to tell whether you've got 0 or infinitely many solutions, guys. Alright, let's move right along now. We've got an example. Okay, let's see. We've got to say, explain why the simultaneous equations 2x plus 3y equals 6 and 4x plus 6y equals 24 have no solutions. Well, I can tell you at a glance why that is the case. The proportion of this to this, okay, 2 is to 3, that's also a 2 is to 3, therefore those lines are parallel. Furthermore, if you look at this, now if you divided through by the y-intercept, right, the y coefficient, that would be 2/3 x plus 1y equals 2. That would be 2/3 x plus 1y equals 4. So if that was a 2 and that's a 4, therefore the y-intercepts are different, therefore you've got no solution. It's as simple as that, but I'll go through all the motions to show you. Dividing by the y coefficient in both equations, you get 2/3 of x plus 1y equals 2, and you get 2/3 of x plus 1y equals 4. Okay, look, gradients are the same, y-intercepts are different, therefore these are parallel lines which will never meet. Bingo! Alternatively, if you put both equations in y equals mx plus c form, just to make it a bit easier for you to see, you get that, and you get that, which gives you a very, very obvious answer. See, look, same gradient, different y-intercepts, yeah? So, yeah, parallel lines, they can't meet. Alternatively, if you want to use matrices, yes, we could use matrices. You would put the equations in matrix form like that, and you would work out the determinant of the beast, which is this thing. Yeah, if you let A equal that thing, then the determinant of A equals that, which is going to be 0. Of course it's going to be 0. So therefore, hence A is a singular matrix, and there is either no solution or infinitely many solutions. We don't know which until we basically go into a little bit more detail and examine those equations closely, which is what I did over here anyway, okay? So going back to the two original equations, dividing by the y coefficients of both equations, which is what I did on the left-hand side anyway, I'm just repeating that process. You get that, don't you? Yes. Therefore, yes, that's the same, and therefore, yes, that's different. Therefore, yeah, they're parallel lines which never meet. But all you'll get from the matrix equations determinant thingy is you'll just get a 0, which tells you there's either no solutions or there's infinitely many solutions. It doesn't tell you any more than that per se, until you analyse what's going on, okay? Which is what I was just doing here. Okay, now what's this? Two simultaneous equations. Oh, of course they have infinitely many solutions. Describe these solutions through the use of a parameter. Alright, well you can see they're the same equation, can't you? 2x plus 3y equals 6, 4x plus 6y equals 12. That's just multiplied by 2 compared to this one, right? Now we've got to use a parameter to describe the solutions. Well, we know there's infinitely many solutions, so it's not uniquely, there's no unique solution, okay? So I'll show you. 2x plus 3y equals 6, 4x plus 6y equals 12. These are the same equation as is found by dividing equation 2 by 2. Now, there's infinitely many solutions. Now, a parameter, ladies and gentlemen, this is often very poorly understood. This parameter thing, the calculator spits out these parameters and confuses everybody no end. A parameter is simply, it is simply a device used to describe multiple solutions when the solution is not uniquely defined, all right? In this case, every value of x and its corresponding value of y, as defined by the rule, and there is only one rule there, are solutions, right? So you pick yourself an x value, you pick any x value, plug it into the rule, and you'll get the y value which belongs to it, which is a solution. Because these two lines are on top of each other. You know what I mean? Okay, so choosing a specific value of x, say n we could call it, if you like, then the y value belonging to n is found by the rule. So 2n, right, if that's our specific value of x, plus 3y equals 6, right? Because you've got to pick a value of x to get the value of y that belongs to it, because there's zillions of them. In fact, there's infinitely many, right? X, y pairs as solutions. So, therefore, if we get that solved, we'll get y as minus 2/3 of n plus 2, where n could be any real number, because these equations work for any real numbers, okay? Yes? So n could be any real number. So n is known as a parameter. That's all we're saying. That's all we're saying. Because there's no unique solution, as I've said about 15 times. So if you try to do it on CAS, right, this is what will happen. Ready? Ready for this? Okay, so you'll get this situation here, where I've done the solve statement there, solve this one and solve this one for x and y, and you'll get this beastly looking thing here which confuses everybody like crazy. So it's saying y is just, you pick your value of y, it's saying, you pick a value of y, it's called it C1, then your value of x will be, plug that particular value of C1 in, whatever it is, and that'll get you your x value. That's all it's saying. And if I do the same thing, reversing the order of these variables here, y comma x, then it'll give me it'll say, okay, you pick your x as a parameter and I'll give you y. That is the solution, which is exactly the same thing as I've got up there. Okay? It is. If you work it out, it is. Okay, I know these things have pretty freaky ways of expressing things. It's just basically the way their operating systems are designed. But that's the same equation as that. It is the same. Alright? Are you happy? I hope you're happy, because this stuff should all start to make a bit more sense to you now. Hence, yes, here C1 and C2 are parameters generated by the little beastly CAS handheld device. Alright? Okay, I think that's it. Now, the next, I'm not going on, the next video will be part 2 of this exciting thing, solving systems of linear simultaneous equations in 2 variables. Alright, so you go and do some practice, and this stuff is the business end. This stuff is the business end of the exam style questions they tend to ask in this whole area. So this is where we're leading to, okay? Alright, we'll see you later.